All right, section 5.2, the mean value theorem. This one's going to be a big one and an important one, so definitely pay attention. We're going to start right away with a word problem that you could probably figure out on your own. I might encourage you to pause the video and give this one a try. All right, it says, imagine I went on a road trip and the distance in miles I traveled could be modeled by this equation. D equals 50t plus the sine of t, where t is the hours I spent traveling. The first question asks for my average speed from time t equals 0 to time t equals 3. We should hopefully remember that we can find average rate of change. So average rate of change, again, is just that equation for slope, right? F of b minus f of a all over b minus a. In this case, it would be f of 3 minus f of 0 all over 3 minus 0. Plug those numbers in, you get your average rate of change. All right, I ended up getting 50.047 miles per hour. You will note I was accurate to 3 decimal places. Always in calculus, try to make sure you're accurate to 3 decimal places. If you're not, you'll probably be marked wrong. Also note, if you didn't get that number, your calculator may be set to degrees instead of radians. Remember, whenever we're doing trig functions in calculus, we are in radians. All right. The big part here is actually this question. Was I ever going exactly that speed? And how do you know? The answer is yes. Absolutely you were. And if you imagine it, if you were driving in a car and you were only going 45 miles per hour and your average was just over 50, at some point you're going to have to cross 50 to go to 60, to go a little bit faster, right? So yes, I was going exactly that speed at some point. Turns out that this reasoning works for all functions, not just functions of distance and speed. And that's actually the essence of what is known as the mean value theorem. So the mean value theorem says that as long as you know f is continuous, in other words, no breaks in the graph, and it's differentiable on the open interval AB, then there's at least some point C such that this equation is true. And the important thing to realize with this equation is what each of these things measure. This on the left, that's a derivative at C, that's instantaneous rate of change. That part of the equation on the right, that's average rate of change. So the mean value theorem says that as long as you know your function's continuous, no breaks in the graph, there's going to be some point where the instantaneous rate of change is equal to the average rate of change. That's the mean value theorem. All right, this page here it shows just the same thing. It shows the mean value theorem, just another way of thinking of it. It says as long as you know your function is continuous and differentiable, then if you pick any 2 points, the average rate of change, which should be the same as that average slope, is going to be the same as the instantaneous rate of change somewhere. In this case, it was right there, right? So it's just saying your average slope is going to be equal to your instantaneous slope at some point, as long as you know this function is continuous and differentiable. All right, let's give this one a try. Consider the function x cubed minus 1 on the interval 0 to 2. Does the mean value theorem apply in this situation? Well, I know x cubed minus 1 is continuous, right? It looks something like that. I know it's differentiable, so the answer is yes, it absolutely does apply. If so, find the C that satisfies that formula, the mean value theorem. And that's not a problem. We just do this separately. Average rate of change from 0 to 2 would be f of 2 minus f of 0 all over 2 minus 0. That would be 7 minus negative 1 all over 2, which is the same thing as 4, right? 8 divided by 2. All right, so my average rate of change was 4. That means because the mean value theorem applies, there is some C where the instantaneous rate of change is also 4. Well, this stands for the derivative. We know how to do that. F prime of x would be 3x squared minus 1. And what this mean value theorem essentially says is there's some C where this instantaneous rate of change is the same as the average rate of change. There's some C where those two things are equal. So to find that C, just set them equal to each other. Some people like putting a C in place for the x, so that's actually f of c instead of f of x. I don't care. You can use x, you can use c. It works either way. I'm going to use x. Set it equal to 4. All right. I end up getting the c is equal to plus or minus the square root of 5/3. You can definitely leave your answer in that form. You don't have to put in a calculator around it. However, that is 2 answers. Only one of them actually applies. I was looking for an answer on the interval from 0 to 2. The only one of those numbers that are on the interval from 0 to 2 would be the positive square root of 5/3. So in this particular case, my c should equal the square root of 5/3, whatever that happens to be. I'm just going to leave my answer in that form. That's where the instantaneous rate of change is the same as the average rate of change. All right. This just talks about the mean value theorem again. It only applies when f of x is continuous and differentiable. I have another type of problem. This one, the mean value theorem is not going to apply. See if you can figure out why. All right, hopefully you did it. Absolute value of x is continuous, but it's not differentiable over that interval. At 0, there is a corner. Not differentiable means the mean value theorem does not apply, which means there is no guarantee that the instantaneous rate of change is going to equal the average rate of change over the interval. So I don't even need to bother answering this question because the mean value theorem didn't apply. I can't guarantee that's true. All right. Some implications of the mean value theorem. One of the biggest ones is actually going to be something called the first derivative test, which we're going to kind of actually start doing today, and we'll formalize it in a couple of days. All right. Increasing and decreasing functions. One of the implications of the mean value theorem basically says that if f prime is positive, then f is increasing. Meaning is that if you got a positive derivative, you are going up, right? Positive slope. If f prime is negative, then f is decreasing. So if you've got a negative slope, you're decreasing. Should seem kind of obvious. The mean value theorem is one of the things that kind of says, yes, this is definitely true. And it's true for that entire section, as long as f is continuous and differentiable. And we're going to talk about that. What it really helps us do, it helps us find extrema without having to graph, which is one of the things I said we were going to learn in the last couple of videos. So we're going to do it with this one. I'm actually going to answer B and C first. I'm going to answer where this function is increasing, where this function is decreasing. If I want to know when f is increasing or decreasing, I just need to look at the derivative. All right. F prime of x is equal to 2x minus 1. I want to know when that thing is positive or when it's negative. To do that, I'm actually going to figure out when it's equal to 0. The derivative is equal to 0 at 1/2. The reason that's important is the only way I can switch from a positive value to a negative value is if at some point I am equal to 0, or if at some point I am discontinuous, right? So I'm going to put in a test value. Let's put in something like 0. 0 is less than 1/2. If I put a 0 into this function, 2 times 0 minus 1, that's negative. That means the derivative is negative for all values that are less than 1/2. If I put something more than 1/2 in here, like a 5, if I put a 5 into there, 2 times 5 is 10, minus 1 is 9, that's a positive number. That means my f prime is positive for all numbers greater than 1/2. This thing here is something called a sign chart. You might recognize it from last year in pre-calc. What that sign chart helps do for me is it tells me when the derivative is positive and when it's negative. Looks like it's negative whenever x is less than 1/2 and positive whenever x is greater than 1/2. So I can answer B and C. So it's increasing over the interval from 1/2 to infinity. Please note, you can use a bracket from 1/2 or a parentheses. It works either way. It depends on your definition of increasing. I don't have time to talk about that in the video, but just know that this could be a bracket around the 1/2 or a parenthesis, and you'd be correct either way. C, when is it the function decreasing? Well, that's when the derivative is negative. So from negative infinity to 1/2. And the important part, local extrema. Well, if I go from a decreasing function to an increasing function, that means I'm going to have a minimum right where I change, right? Where you go from decreasing to increasing, that's going to be a minimum. So I know for A, doing it in opposite order, I have a minimum at the point 1/2 comma something. How do you find that comma something? Plug the 1/2 back into your original equation. Ends up being negative 12.25. That kind of annoys me that I am mixing decimals and fractions. I don't tend to like to do that. Let's fix that. You might want to give this one a try. If so, pause the video, give it a try. All right, we're going to do the same thing. We're going to answer B and C first. So I need to find the derivative. I want to find where that derivative is equal to 0 or undefined. Those are critical points you might remember. All right, my derivative is equal to 0 at a plus and minus 1. So then I'm going to make this sign chart. And I'm going to test values between each of those areas. All right, if I put a value less than -1, like -10, into my derivative, I will get a positive number. And so that entire section will have a positive derivative over that section. If I put something between -1 and 1 in there, like 0, plug 0 into this thing, I get a negative number. So my derivative is negative over that section. If I put something more than 1, like 10, into this function, I get a positive number. So over this section, my derivative is positive. All right, B. When am I increasing? I'm increasing when my derivative is positive. So over this section and that section. Negative infinity to -1 union 1 to infinity. When is my function decreasing? That's when my derivative is negative, from -1 to 1. And then again, I'm answering A last. Where are my local extrema? Well, I can see that my function starts by increasing. At -1, it changes and starts decreasing. At 1, it changes again and starts increasing. So I'm going to have a maximum at -1 and a minimum at 1. How do I find the y values again? Plug the number into the original, right? This thing gives me points. That thing gives me slopes. I want to know the point where my maximum is. So take that -1 and plug it in there to figure out your maximum value. Looks like I'll have a maximum at -1 comma 12. Plugging a 1 in, I'll have a minimum at 1 comma 8. All right, one last problem. This would be an important one to do, and then we're done. All right, same thing. We're going to find the derivative to find where I'm increasing and where I'm decreasing. If I were doing this problem, sorry, you could find the derivative using the quotient rule. If it were me, though, I would probably rewrite it like this, because then the derivative is so much quicker. If you want, you can rewrite that like this. Means the same thing. Now, again, I care where my derivative is 0 or undefined. Those are my critical points, and those are the only places that local extrema can happen. You might remember that from a couple of days ago, right? Local extrema can only happen at critical points. In this case, my function is never equal to 0, but my function is undefined at 0, right? If I plug a 0 in, I'm dividing by 0. So the only critical point I have is at 0. All right, put in some test values, put in some negative number into my derivative to check what if the derivative is positive or negative there. Let's see, if I put a negative in there, I'll definitely have a positive value. If I put a positive number into this thing, then the end result is a negative value. And I can answer my questions. All right, I'm increasing when the derivative is positive, so from -infinity to 0. Decreasing when the derivative is negative, so from 0 to infinity. And then this is the important part, the local extrema. It would be very, very tempting to say there is a maximum at 0 comma something, because I can see my derivatives going from increasing to decreasing. I'm like, hey, that's probably a maximum. But be careful. If you plug in a 0 into my original function, you get 1 over 0, which is undefined. I can't have a maximum at 0 comma undefined. That doesn't make any sense. This function doesn't actually have a maximum, because the only place where I would have a maximum, the function is actually undefined. So there is no maximum or minimum with this. If you graphed that function, it would look like this, right? Increasing, decreasing, right? But there's no maximum there because I'm not defined at 0. All right. Section 5.2.1, I've got 4 problems that are on the mean value theorem, 6 that are kind of like these ones. Please note at this point, we are going to start doing the shaded gray problems without a calculator. So if it's shaded gray, do it without a calculator. See you later.